Data Viz Friday. Welcome, everybody. We are so happy to have you here. This week, we are talking all about Scatterplots. We have a new face here on the stream today. Dave, as we mentioned last week, is on vacation. He is out skiing and having the time of his life with his family. And we have Noel here with us, and Team Notable, Michelle and Elijah as well. I'll kick it over to Noel to give her a brief intro on who she is and her background and whatnot. But I wanted to just take a second and thank everybody for joining us. I think this is our 4th or 5th Data Viz Friday, and they've been fun for us. We've had great conversations with folks who have tuned in. And so as we kind of get this point, we'd love to get some feedback. What do you like? What are your recommendations? So if you have some feedback, please send us a DM, leave a comment. We'd love to hear what you think about the show. And we're going to start doing a rotation. So we have Noel this week. You'll start seeing more faces from the team. We'd love for folks to meet more folks on our side that have really, cool work that they're working on and interesting background. So with that, let me send it over to Noel.
Yeah, thanks, Michelle. Hi, everybody. I'm Noel Cothran, and I'm a front-end engineer here at Notable. And I've been working a little bit on our data visualization product, DEX. And I come from a non-traditional tech background. So I actually studied fine arts as my bachelor's degree, and then education in a master's, and was a teacher for a little while, but started to learn HTML and CSS and kind of pivoted into tech later in life. So that's kind of a unique intro to how I got here at Notable.
And we're lucky for
the only person, yeah.
Yeah, no, we're extremely lucky. Noel's a talented front-end engineer, has done a lot to make the product better. Yeah, Noel and I talk about this a bit because my background, for some of you who know me, but for others, my background was in philosophy. I studied philosophy in my undergraduate, and then I studied Chinese history in graduate school. And so I went in the same direction that Noel did, away from arts and humanities and into tech. And we always joke about it because my wife has a degree in physics and a graduate degree in international history, and now she's an artist. And so we're just ships passing in the night, going back and forth. So Michelle, do you have a similar strange path?
I wish I was cool and unique like that. No, I went to school to study business and marketing, and I've done business and marketing. But this gives me hope that perhaps artistry or something exciting, could be in my future, and I could pivot somewhere maybe a little bit cooler. I don't know.
Definitely. No, we need business and marketing too. So.
All right, let's I think we've got a good group of folks here. So Elijah, let me kick it over to you to get things going.
Wonderful, thanks everyone. And I can see 9 people in the notebook, which is great. We've got penguins and roosters and squirrels and bulls and Noel. So I'm excited to have folks join us. This time we're going to be talking about Scatterplots. And Michelle did mention that we'd love feedback on what we talk about, what we get into. And if you wait until the end of this stream, we're actually going to be talking a bit about next week's special Data Viz Friday on a special time, actually on a Thursday. We're going to be introducing a whole brand new feature of the product that deals with automatic data visualization. And so we'll show a little bit of that at the end of the stream, but also in doing so, we're going to show a lot of different charts. And so maybe you'll see some charts that you want to know more about, and you can tell us that that's something you'd love for us to focus on in future iterations of this. So with that said, I wanted to get into Scatterplots. Scatterplots not something that I think I need to introduce to anyone who's had any experience doing business analytics or data science. Scatterplot's a pretty meat and potatoes chart. But I wanted to get into it just like we did with bar charts, because there are a lot of features to Scatterplots and techniques and approaches that you might find that you're not aware of, or that you're not quite sure how to use effectively. So we're gonna dive into that. So here's the notebook that we've shared. This is an interactive notebook. It's the Notable product. You don't have to use Notable to make Scatterplots, of course. So pretty much anything that I'm showing off here, you can do with whatever tool or library that you use to make your charts. Now, last week we dealt with some pretty shady data at its source, and then shady data as passed through to us from ChatGPT. So this time I thought we'd shift gears and deal with some very classic data sets. So we're going to talk about 3 data sets as we're looking at Scatterplot. Those 3 data sets are really sort of the classic data sets that you see to demo Scatterplots or to use for machine learning to look at correlation and identify clustering. Now, what does a Scatterplot do? Scatterplot fundamentally plots points in what we call Cartesian space. Cartesian space is just a fancy way of saying an XY plane, right? Like you put points on a plane where the X coordinate and the Y coordinate correspond with some data value, what we refer to in data visualization as encoding. You're encoding a data value onto its X position, and you're encoding another data value onto its Y position. Like I just said, I have a background in philosophy. So for me, Descartes is all about, cogito ergo sum. But for mathematicians and for data visualization, Descartes is all about formalizing this concept of that XY plane. What else do Scatterplots do besides allow me to talk about Descartes? They let you encode another value into the size of the circle. So if you wanted to change the size of the circle, then it would be a graduated symbol plot. There, you can color those points. And so you could color those points based on the category that those points are in, or you could color it based on another metric using quantitative coloring. That's enough talking about it. This is data visualization. Let's look at what we mean. So your basic scatter plot, and this is that iris data set. So we've got about 150 irises. They are measured by their petal width and petal length, their sepal width and sepal length. And I think Noel left a really nice little comment in here that showed a picture of this, right? So what do we mean by petal and sepal? Well, here's an iris. I'm not much of an iris person, but here's an iris showing off what we're talking about. So they've measured these individual specimens, and then they've also decorated the data. Let's take a look at the data. They've measured the sepal and petal dimensions, and they've told you which variety that specimen is from. And so then we can go and plot that, for instance, petal length and petal width, and we can see that petal length and petal width are pretty strongly correlated with each other, meaning that as one goes up, the other goes up, and as one goes down, the other goes down. And then if we wanted to, as I said above, we could encode another metric onto the size of the circle, turn this into a graduated symbol plot. So now we've added sepal width, and we can see that while petal width and petal length are strongly correlated, there are some interesting outliers as far as sepal width. So you can see that, by which I mean you look at the chart and you can notice that there are some large circles and small circles. And when you see that, that's how we identify sort of the value of that data attribute that we're encoding. So we could take a relatively simple chart and make it a bit more complex by using graduated symbols. And then we could also color that data set, because of course what we're trying to do with this data is we're trying to identify correlation, but we're also trying to identify clustering. Is there something about the categories of the data that is meaningful based on the metrics of the data? And we can quite clearly see that of these 3 varieties of iris, that they have very strong clusters that correspond to the variety. So in red here, I have versicolor, and you can see that it's in the middle. It's got a moderate petal width and petal length. You can see Setosa is down here. It's got much smaller petals, clearly. And then up at the top, you've got Virginica, which has much larger petals. And you can see that there is a region here now where there is some overlap between the versicolor and Virginica varieties. And that's an interesting pattern in clustering of the data that we can immediately spot. Just plotting a scatter plot, we didn't have to use the graduated symbols here, and coloring it by category. Now we could use color to encode quantitative values. So we could encode, in this case, sepal length using a color from red to green. And what I've done here in this quantitative color is to not use a gradient, which is a continuous color. We think of the very popular viridis gradient, which goes from purple to yellow, that is very popular in data science. Instead, I've used a threshold for my color, so that if it's within a certain set of values, it falls into a threshold that we encode as red, then orange, then yellow, then green, then dark green. And the reason why we use thresholded colors is because when you have a gradient, it's hard to tell the difference between, say, a slightly dark purple and a slightly lighter purple. Whereas thresholds highlight, and especially if you're using a thresholded color scale that's designed to be distinctive, like this one. This one comes from Cynthia Brewer's Color Brewer family of color schemes. It's very easy now to see when something passes that threshold. So suddenly it jumps out at us that this particular iris has a sepal length that seems particularly small for where it sits within the data set plotted on Scatterplot. So you can use gradients for coloring scatter plots. You can use gradients for coloring large data sets, but you want to make sure that when you're using gradients versus thresholds, that you're really using that for exploratory data analysis. So when you are individually exploring a data set and you're looking at some value that you're encoding with color, gradients are great because you're highly invested, your eyes are getting accustomed to that gradient shift, and you probably have stronger understandings and context about the data set. So it's going to be helpful for you to deal with, hypothesis generation, hypothesis validation, whatever you're doing in that exploratory mode. But when you're presenting, when you're creating data visualization for explanatory data graphics, you're presenting this to an audience, I'd suggest really, trying hard to use thresholded color schemes, because it's going to be easier for your audience to understand and make meaning out of that color if they are quantitative thresholds. And you can use all sorts of different kinds of thresholds. I'm not going to get into that in detail here, but we expose quantiles. You can have very simple thresholds that are based on just sort of breaks in the data that are like, if you had a value between 1 and 10, you could break it at 2, 3, 4, 5, 6, etc. Or you could use something more advanced like CK means, which just finds natural clusters in your data. Or you could use semantic thresholds, which are something that are very important that people underutilize. And by semantic thresholds, what I mean is that you understand, as the domain expert, that once it crosses this threshold, it has some kind of meaningful value. So it could be that it's hard to say with a data set like this, but you could say something like, we'll see the wine data set below. If it's above some certain alcohol content, maybe it qualifies as a different kind of wine, or it has to be labeled different. And so that might not show up in the data per se. It might not be labeled as a category, but you know it as a semantically meaningful threshold. And you could define that and use color to define that. We did that last week when we defined some thresholds with the bar charts that were semantically meaningful. I had created some kind of value where the faculty rating was above some certain value. We colored it green. Below some certain value, I colored it red. So that's how we would use color and graduated symbols on a simple scatter plot. And that's
I'll just
relatively straightforward. Oh, go ahead. Yeah.
For a second, Elijah,
Go ahead,
because I love seeing those two charts next to each other, and the fact that you can view them next to each other really does add to your ability to understand the data. You see the kind of in the middle on the left side, I guess, everything's red, that's the versicolor. But when you look over to the right chart, you see that versicolor actually has a variety of sepal lengths. And I just like the contrast of those two together. And I also really appreciate, scatterplots are my favorite charts because I think they're really beautiful and they can encode a lot. And so I just wanted to appreciate the contrast of these two charts with the different types of coloring together.
I mean, you make a great point, and one we're going to get into in more detail below. It's that a chart that you decide to have, even if it's a data set, if you pair it with the same chart and you're encoding almost the same data, but you encode maybe, in this case, a category and contrast it with a metric, the chart becomes more powerful, right? We don't always have to think about like, well, what other data set could I bring into this, or what more complex, how many encodings can I pack onto a single chart? pairing charts, even if it's with itself, and a slight variation is great for understanding the data better, because the data acts as its own context and provides you with this raw material for generating hypotheses, right? People typically use data sets like this, Noel, to understand clustering. But one of the things you could really dig into is, why is it that this variety has so much more variation? Does it have more variation, right? Is this an artifact of the way we've colored it? Once you apply some sort of statistical measures to it, you might find out that it's statistically actually not significant, or you might, but you're absolutely right. There is so much more color variation in this quantitative scale in this region. And we know, because we're looking over here and it's immediately on screen. We have no visual memory. If this was on one screen and then I had to flip to the other in a tab, it would be hard to keep track of that. We know that that's a single variety, and that does lead to this interesting hypothesis generation, which is the value in EDA of charts like a scatterplot. And you're right, they're quite pretty, aren't they? So this is a smaller data set. It's about 150 points. It's pretty easy to plot and think about how we could encode, I can encode 4 different values simultaneously. That's a lot to put in front of a person, 4 different metrics at the same time, or 3 metrics in the dimension over here. But because it's a relatively small data set, the human eye can differentiate, and you can come up with interesting stories and hypotheses about it. But what happens when we work with larger data sets? So there's another classic data set. It's this diamond data set. It's around 54,000 diamonds, each of them measured by their size, their weight, their price. And we've got all of the different values that we're tracking in this table. And when we put 50,000 points onto a screen, we run into more issues. Now, this is a subset. Let me go down and show you. This is the full data set here. Here's 50,000 points. Now, I can see, because I've colored in a certain way, I can see certain patterns, but you can see that there's a lot of data here. And what you run into with large data sets is what they call the overdraw problem with scatter plots, and any data set where you're plotting points, where those points could be drawn on top of each other. And you'll see people use a opacity to show the points accreting on top of each other. So you could have something so that the points were all semi-transparent, and you would see a density naturally occur as those transparencies build up on top of each other. But that actually has its own issues, because how transparent objects combine is not a simple fixed thing. For those of us, Noel, you and I, who have experience with graphics, we know that there are different ways, whether you do a dissolve or you do the multiply, or how you decide different transparent things should combine. And if you're just using the defaults and you're not even aware how they're combined, then what you're doing is you're giving a rough picture of density, and you're offloading onto your reader either, and I wouldn't say incorrect, but maybe incomplete picture of the data. But you're also offloading onto them processing that density to know what it means. So some of the tools we can use to address that, I've put a little threshold annotation here at the 1.5 carat mark, because I'm going to talk about that. But some of the tools we can use is to use marginal graphics. So marginal graphics, this is this simple histogram in the margin. That's why they're called marginal graphics. So this is a histogram of density of points just along the x-axis, just along the price axis. So what I've plotted here is carat weight by price of a subset of this data between $14,000 and $19,000, and between 1 and 2 carats. And the marginal graphics tell me that the distribution of price is kind of what we would expect. There's more data here. Even if you couldn't tell, you could see that it's pretty dense, but this actually tells you precisely how dense the data is along the x-axis. And then you can see along the y-axis the density of the carat weight. And you can use that to show density. You can also use what's called a contour plot. So contours come out of cartography and GIS to show the magnitude of elevation for mountains and hills, each contour indicating a meaningful shift in density In the case of hills and mountains, that density is the value of the elevation. In the case of our data set here, it's the number of points. And so we can see that the densest spot here is in this area around 1.5 carats and around $14,500. But we also see that there's dense areas here along the 2 carat axis, and there's a relatively dense spot out here in this $17,000 range around 1.75 carats. And so that density, now again, this isn't showing the exact numbers along the contours, but it is helping to orient the reader to not just try to squint and come up with their own sense of density, but to give them some idea of the density in a very large scatter plot. And these are methods you can use to address that overdraw problem. So one of the patterns that we might see then in a large data set like this, when we're looking at density, is we see this really interesting distribution along carat weight. Along price, we see what seems to be a distribution we might expect. But carat weight shows 2 very exciting peaks, right? It's this bimodal distribution where the majority of the diamonds seem to be clustered around 1.5 carats and around 2 carats, with very few diamonds below that 1.5 carat weight. And the diamonds that are below it seem to have similar characteristics. And you might ask yourself, well, why is that? And it's because diamonds, when people purchase diamonds, people don't purchase diamonds as data scientists. People purchase diamonds as human beings. And what people who cut diamonds know is that a 1.5 carat diamond is worth a lot more than a 1.48 carat diamond. And that's what this data set shows us. We see that at this 1.5 carat mark, you see a lot of diamonds. Now we're encoding the clarity of the diamond. I'm not going to go through all these clarity values, but IF means internally flawless. And then all of the rest of them mean having some kind of flaws. There's some kind of occlusions to greater and greater degrees. And so what we see is that below this line, we get a lot of internally flawless diamonds. And then we get a lot of very poor grade diamonds. So what that tells us, or a hypothesis that you might have about this, because I am not a diamond expert, but what I see when I read this data set is that if you can cut a diamond that's 1.5, that's around that 1.5 carat mark, and it is not just a garbage diamond once you've cut it, then you're going to cut it to be 1.5 carats. Whereas if it's going to fall below that 1.5 carat mark, you're going to do that for a diamond where maybe you cut it a bit smaller, but it's what's left of the diamond is internally flawless, because what you're cutting out is the bad parts of the diamond, right? The occluded parts of the diamond. Or it's a garbage diamond. I shouldn't say garbage, but it's a highly occluded diamond that it's not going to matter once you've cut it out, that it's going to, you're trying to make the best of it. And that happens at this 1.5 carat mark significantly. And then it happens again at the 2 carat mark, because again, if you receive a diamond ring and the diamond ring you receive is a 1.97 carat diamond, that is not 1.5% worse than a 2 carat diamond, right? If you get a 2 carat diamond, it's probably twice as good as a 1.97 carat diamond. And that data set reflects it. And then you see some interesting things about the price of these diamonds that does not seem to track with their with how internally how occluded they are. So then you have another interesting place to dig into the data set to find out why the price doesn't seem to correspond with that the quality of the diamond.
Our friends at Dagster gave us a nice comment here saying another great example is the distribution of marathon finishing times.
Oh, and yes, of course. No, there are some very interesting distributions of marathon finishing times. There are interesting distributions of people passing tests when the test is some kind of required test for some kind of certification. These distributions can indicate human qualities in ways that you might not expect from data sets that I don't want to get into in too much detail because I want to focus on the scatter plots, but absolutely we should do marathon times as a data set in a later talk, in a later Data Viz Friday. In fact, it would be great for the dot plots. Yeah. And maybe if it's got geodata, we could also plot it on a map. That would be fun. So other things we can do with large data sets. So you'll notice, first of all, what I wanted to do was point out that marginal graphics aren't just histograms. Marginal graphics are any summary distribution you could put in the margin. So for DEX, this tool that we use that's built into the Notable notebook, it's a no-code data visualization tool, and it exposes a lot of summary visualizations that you can use on their own. And all of those summary visualizations are available as marginal graphics. So you might use a marginal graphics that are a histogram, like I used above, because that suits the data. Or you might use marginal graphics that are box plots or violin plots or heat maps or other kinds of marginal graphics. It depends on the fit for the data. It also depends on the audience, right? If you're dealing with an audience that isn't familiar with box plots, it can be very intimidating. If you're dealing with an audience that is familiar with them, they can be extremely powerful. So what's really exciting about this is you cannot tell at all, but this area here is the median density. This is the middle of the data set. You can't tell that by looking at it, but you can tell that in the box plot because it's got the median line right at the center there. And the majority of the data exists within the fat part of the box plot. So the majority of the data is in this small region over here. And you just can't tell because of that overdraw problem. So that's why marginal graphics are super helpful. I've got an annotation over here that's pointing out some particular diamond, this yellow diamond over here. We just updated the features and it's not available in production to show the annotations in both the zoom in chart and the base chart on the left. But you see, I've got this shaded region that I'm zoomed into here. And I could open up the controls and I could manipulate the zoom, but I don't want to get too far into that because we've already talked a bit about it. But being able to brush the data set and zoom into particular areas, that's not just valuable for exploratory data analysis. To get back to what Noel brought up, it allows a user who's looking at explanatory data graphics to bring context to the data visualization, to the chart. So by zooming into this region, I now have this dynamic context for the whole chart, and I can see some kind of distribution here that is not visible, that 2-carat cutoff line. It doesn't appear very clearly here, but it appears very clearly once I've zoomed into it. I've got a different distribution here now. You can see the distribution is right in the center. So at this point, the distribution of prices seems like more of a normal distribution when you're in this area. And there's just a lot of there's a lot of value to providing that zoom, that brush zoom, that is one of the reasons why we implemented it as a feature for large data sets.
Okay, now I can see that the data set above was filtered, so we were only looking at above a certain price, between 1 and 2 carats. That makes a lot more sense now to me. Now we see
right.
what
We
all
were
the
looking at
diamonds
this
are. Yeah.
Yeah, we were looking at this square down here between 1 and 2 carats and between $14,000 and $19,000.
Awesome.
The other, it's funny because it's kind of the same thing. I didn't realize we're going to be talking about the same thing over and over again. But all of this falls under this category of what's known as faceting. Faceting is to split the same data set into multiple views. And traditionally, when you deal with faceting, people will talk about faceting by a metric. So here we're looking at another data set, which is wine. This is a data set of varieties of wine that are rated by a bunch of different metrics. I don't drink wine. I don't know much about wine. So this is how I can enjoy wine, is via data. It's probably better this way. But what I've done here is I faceted on the y-axis. So what that means is that I've maintained the alcohol content on the x-axis. The alcohol content you'll see is the same across all 4 of these charts. But I've changed the y-axis. So one y-axis is the measure of flavonoids, another y-axis is the measure of ash, another y-axis is the non-flavonoid phenols, and another y-axis is the malic acid. And this allows me to see, are there any interesting patterns of correlation with alcohol across these different metrics. And what I've done here is I've dropped a trend line onto here in the formula for the trend line. And this particular trend line is a polynomial trend line. It means it bends, it uses multiple points to draw the curve. You probably are more familiar with a traditional linear trend line. We expose all of these different trend lines, exponential trend lines, logarithmic trend lines, and all that in the product. I put the polynomial one in here because it's very interesting, the correlation between flavonoids and alcohol. And you can tell that there are these different correlations or lack of correlation, right, between these different values. And that's why metric fasting is so valuable. Again, going back to what we were talking about with seeing the quantitative coloring and the categorical coloring side by side, seeing the zoomed in and the unfiltered chart side by side, it allows you to see the data as context for itself and evaluate it and generate hypotheses based on that. You can facet by metric. We can also facet by dimension. So if we go back to that chart, the iris data set, we could facet by those different varieties of irises. And that's what I've done here. I've got each variety in its own facet. Now you'll notice that the facets are not sharing the same scales anymore. So you have to keep that in mind. It's a little bit of additional lift on a reader as they're examining it. But it does allow you to look at the distributions within each of these categories to see if there are patterns in the distributions in these categories. And I love when you have a graduated symbol plot, there's a lot of overdraw, you get this jawbreaker effect. This also, you know, when we talk about measurements, right? This is very interesting that all of these varieties of iris are very polite and only grow at rounded points. That's nice that they don't grow at, say, 0.22. They all grow at 0.2 or 0.3. And the joke I'm making, which is probably a dumb joke, is that clearly the person measuring this rounded that to those points. And that might not have been so clear when you were looking at the full data set, but it becomes clear here. And data issues are part of or data caveats, it's not necessarily an issue, are things that you can see once you zoom into different views. But this allows you to compare side by side these different varieties and their distribution of petal, in this case, petal width and petal length side by side. Now, again, the key aspect to faceting when we traditionally think of faceting is that we've maintained all of the other settings except for the setting that we've faceted on. So I'm not showing different values on the X and Y axes. I'm showing the same values. I'm not showing different values on the graduated symbol. I'm encoding the same values. The only thing that I'm changing is the dimension of the data that I'm showing in each chart. Same with over here with the metrics. I'm maintaining the x-axis. If I had used graduated symbols or color, I would have maintained those, and I would have only faceted on the y-axis. And that's what we typically think of when we talk about faceting.
Elijah, would
oh, go ahead, Noah. Yeah.
Keep the scale the same amongst all your facets, or is it kind of not really what's practiced?
There are times to keep the scale unified across facets. It's definitely an important thing to have available, depending on what your question is and who your audience is, because you are adding to the complexity of this by forcing them to remember that the scales are different. So you should really, if you're deploying this and you're not sure, you should provide both options.
Great, thanks.
So if we take faceting and we just say, well, that's a great idea, why don't I just facet everything on this data set, right? Then you get to the point of what's called a Scatterplot Matrix. And so this wine data set has a huge number of, in fact, I'm gonna open up the control. Actually, I'll open up the comments over here, the sidebar, because that'll make it a little bit smaller so that we can hopefully show more of it on screen. It's pretty unreadable at this point, but I'll read it for you. I've got pretty decent eyes still. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 metrics here that's in this wine data set. I only showed 4 plus the plus alcohol. And what a scatterplot matrix has done is said, okay, let's take wine, which is some metric, and alcohol, which is some metric, and malic acid and ash and ACL and et cetera, and compare it across every other metric in the data set. And so immediately what we see is this wine metric is clearly some kind of ID, right? There must be 3 kinds of wine in here because they have 3 distinct distributions along the x-axis. So even though it is technically a metric, it's really a dimension. So immediately we know to treat it as such. And then we can see the correlation between every metric. We can see that hue has a very strong correlation with whatever OD stands for. Unfortunately, not being a wine drinker, that's where I'll run into that problem. Phenols has a very strong correlation with flavonoids, and that's probably why they have this non-phenol flavonoids option here to split them out, and so on. And so we can see the scatter plot, every scatter plots. This is what, 16 by 16, 256 scatter plots. And then on the other side of the matrix, because if we just showed the scatter plots again, we'd be repeating the information. Instead, we're actually just showing the correlation, the R value between them. So that you can look at the trend line, or you can look at the shape of the data, or you could just see the actual value. And then we show some summary statistics in here, so we can know that for phenols, for instance, the median value is 2.36, the mean is 2.3, the min is 0.98, and the max is 398. And so scatterplot matrices like these are really valuable for getting an overview of a data set so that you can understand where to go when exploring it, but also as you can provide as context to an audience, especially an audience that's accustomed to faceting, or you might hear it referred to as small multiples if you're dealing with if you're dealing with analysts. Analysts refer to the technique typically as small multiples. And that's, you know, faceting just as its own chart. Finally, I did an entire notebook on connected scatterplots. The connected scatterplots are a fun topic to address on Twitter because people have very strong opinions about connected scatterplots. But if your data has, for instance, temporal characteristics, if it has dates, then you can plot it as connected scatterplot. So here's presidential approval as a rating, plotted on a scatterplot by conventional gas price. A very simple question, right? Does presidential approval correlate to the price of gas? And it's a challenging question because we know the price of gas increases over time regardless because of inflation. So we could have normalized this based on CPI. But we could plot it and we can get some idea here. And we could use quantitative coloring to color the date value and get some idea there. So we know that from 1990 to 2016, so the purple's in the 90s and the late 2010s is in the yellows. This is that viridis color gradient we referred to earlier. Or we could connect those. We could connect those points based on points in time. So this being the first point in time, and then this being the last point in time. And a connected scatterplot shows you the temporal characteristics as a connection between each point, which we've put arrows on here so you can read it a little bit better. And what's really interesting here is if you, well, I think you don't even have to have an astute eye, you should notice there's a lot fewer points on the connected scatterplot than there are on the scatterplot. And why is that? Well, that's because once you've got a temporal display, you can take advantage of techniques that are suitable for temporal data. And in this case, what I've done is I've smoothed it to the month. I've gotten an average by month, which makes the data a little less messy, maintains the structure of it, makes it a bit more readable. So I'm not going to get any further into connected scatterplots. We might do a connected scatterplot episode at some point, but if you're interested, there's a link to the notebook all about connected scatterplots. And if you really don't want to make friends in data visualization, tweet about connected scatterplots. That'll really help. So that's scatterplots. I hope that the features that we've talked about here, the approaches, especially marginal graphics and scatterplot matrices, but faceting in general, is something that you found useful, that you'll find that there are methods here that are going to make your charts and your plotting, your exploration and your explanation more valuable.
That was great. Thank you, Elijah. I think one of the things that I've gotten from all of these sessions that we've had is that the different types of visualizations really help you tell a different story or help you really learn what the different angles of a story are. And I think that's super valuable for anybody that's, working with data in any form. And so that's something that we've been working on at Notable as well, is how do we enable people to be able to look at data from different angles more easily. And so next week, we're having a special edition of Data Viz Friday. It will actually be Data Viz Thursday. So keep an eye out for that. We'll be doing it on Thursday. We're also going to share something that we've been working on called Data Prism that really helps folks. You think about all the different chart types, the just few that we've covered over the last several weeks. There's even more. How do you use those best? How do you be able to look at the different angles of the data better? And so, Elijah, let me pass it over back to you one more time to maybe give a brief overview, a little sneak peek of what next week will be about. And again, that will be on Thursday next week.
Sure, I appreciate that. So you're right, Michelle. What you were saying was, and I'll switch over to a different data set. You'll notice that now there's suddenly a data prism suggestions over here on the right. We'll get to that. But I wanted to address a really important point you brought up, which is about storytelling. And one of the main challenges with using traditional data visualization libraries and tools is they're really good at providing you with those traditional charts. You can connect them to your data sources, and you can get a chart of your data. And a scatter plot, just a regular scatter plot, is going to help you to understand that data better. But you could see that as we were going through that, we could, just by applying some color, just by applying some other charts as context, start to tell a story, right? I wasn't approaching any of these as data science with a hypothesis in mind or hypothesis generation in mind. But immediately, once you start to use these features, a chart becomes more of a story. And so that's an important feature, like you said, that we've been trying to help folks out with. Another one is to understand their data from these different perspectives. That's why we enabled so many different chart modes in DEX. But we know that faceting is a powerful way of looking at your data and getting context about your data from the data itself. And so one of the things we've done is we said, well, what would faceting look like if instead of just by metric or by dimension or by color, what happens if we facet by different modes of visualization of the data? So what happens if we facet by chart? So I have this data set. It's the happiness data set I used all the time. We've got happiness score and then all of the measurements of these countries that went into calculating this happiness score. If I go over to this data prism option over here, and this will be released soon, what we get is we get a report on our data that has sliced up the data and looked at different views into the data using different charts to show those views, some of which will be familiar because we just talked about bar charts or scatter plots. Some of them may not, like this dumbbell plot. These are the same data presented with these different views here, right? So this is like faceting on chart mode. Maybe a dumbbell plot is going to reveal to me something more valuable about the data that resonates with me or my audience more than, say, a multi-axis bar line chart. And it does more than that, right? It does. We've got those box plots showing up, showing outliers in the data and the distribution across different regions. Again, this is the same data now shown as a box plot versus a tree map. Maybe a radar plot's the right approach for one of these for this data set. And here's our graduated symbol plot showing up. Maybe it turns out there are countries in here, and Data Prism is smart enough to say, hey, these look like country names. We should drop this into a choropleth map. Maybe you've got a whole bunch of metrics, and so we should give a Scatterplot matrix. I just want to point out to folks that I've got my screen kind of small for a presentation, so everything's a little bit smaller and bunched up than it would be on if you use this tool out in the wild. But we provide a lot of different views into the data using the different charts that are available to us in DEX, including complicated charts like parallel coordinate systems that then you could say brush, and you'd watch the rest of your data respond to that. Because these different views into the data, to your point, Michelle, can tell different stories. These different views into the data can afford different modes of analysis. And these different views might not be appropriate because, you know, automated tools aren't always smart about finding the best metrics and the best dimensions. But one of the things that holds us back when it comes to using data visualization is our unfamiliarity with certain modes. And once I see, oh yeah, here's the box plot with that value, and here's a tree map. Oh, so that's what the tree map's doing. Maybe what happens is I go into the tree map and say, well, this tree map was what I wanted, but I didn't want it to be by trust. I wanted it to be by the score or something else. And so by doing that, we can afford our users the sort of ability to start with just a table of data, provide these many different views, not just sort of simple faceting, not just simple charts, but a lot of different sort of robust views into their data, and allow them then to move into the more valuable part of the work, which is identifying stories, finding insights. Why is it that dystopia residual is so different, trends so differently across all of these categories versus Southeastern Asia, right? And then explore that, or then surface that for their users. So we're excited about Data Prism. It's coming, and I'm glad for the folks who stayed for the live stream to get a sneak preview of that.
Yep. So if that's interesting to you, and it's super interesting to me, tune in next Thursday for our Data Viz Thursday, where we'll be covering that in more depth, and we'll be taking questions, and it will be a great session. So thank you everybody for joining us. We will see you next week. Take care.